Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial on basic vibration behavior of machinery subjected to shaft misalignment will discuss information that will hopefully assist anyone who is responsible for installing or maintaining rotating machinery, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So, this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. The major topics that will be discussed in this tutorial will start off analyzing the two basic types of forces that act on our rotating machinery. Static and dynamic forces were mentioned in the first tutorial in this training series, but we will take a look at the relation and interaction between them here. An abbreviated list of some of the problems that can be identified using vibration analysis as a non-destructive diagnostic tool will be covered, as well as a list of problems that typically cannot be identified using vibration analysis. A discussion on the natural elastic behavior of shafts will be covered, and how elastic bending occurs under misalignment conditions. Results from two controlled misalignment studies will be presented that will illustrate what happens to the overall vibration on misaligned rotating equipment. If you were to ask, what does shaft misalignment look like on running rotating machinery? A large percentage of the people currently working as vibration analysts would answer that vibration due to a shaft misalignment condition will exhibit vibration running speed and twice running speed frequencies. The axial vibration levels will often be higher than the radial vibration levels, and there will be a 180-degree phase shift across the coupling. Is this true? Will this always happen? First, let's discuss what happens to the overall vibration on misaligned machinery. How would you answer this question? If you carefully align a drive system, start it up, measure and record the vibration levels, then shut it down, intentionally misalign it, start it back up, and measure and record the vibration levels again under a misalignment condition, what will happen to the amount of vibration? Will the vibration go up? Will the vibration go down? Or will the vibration stay the same? That's a pretty interesting question, isn't it? Let's start figuring out what causes vibration to occur in the first place. As we discussed in the introductory tutorial, forces that are periodic and repetitive in nature are defined as dynamic forces. A classic example of a dynamic force is an out-of-balance condition. At some point on a rotor, a heavy spot may exist. The instant rotation starts, the heavy spot changes its angular position and begins producing a centrifugal force. Even though the frames and casings of our machinery are fabricated from metal, metal is elastic and will deflect when a force is applied to it. Since the direction of the force is continually changing, the elastic support that is trying to hold the shaft in a stable position is responding to the centrifugal force acting on it and consequently deforms elastically. This repetitive elastic deformation from the circulating centrifugal force is referred to as vibration. Other problems that can cause dynamic forces are eccentric sheaves, damaged bearings, damaged belts, or improper meshing of gears, to name a few. What is vitally important to understand is the only types of forces that can cause vibration are dynamic forces. By definition, static forces always act in one direction. A classic example of a static force is the downward force on a bearing due to the weight of the shaft. Another example of something that puts static forces in a bearing is belt tension. Keep in mind that the bearings on the motor and fan are seeing forces from two different mechanisms on belt-driven machinery. Not only are the bearings seeing the downward force due to the weight of their shafts, but now an additional force from belt tension is present. Another classic example of a situation that will produce static forces on bearings is a shaft misalignment condition. These are three very common sources for loads on bearings. Also be aware that static forces are continually present, whether the machine is running or not. It is important for you to remember that dynamic and static forces can and do exist at the same time. Here is a list of the most common sources for vibration in rotating machinery. Out of balance conditions, damaged rolling element bearings, damaged or eccentric gears, and loose parts are very common causes. Resonance refers to elevated vibration levels due to a dynamic force exciting the natural frequency of a machine. Shaft or bearing misalignment, bent shafts, excessive runout, damaged belts, rubs, and hydraulic or aerodynamic forces also contribute to vibration in machinery. These are very serious problems that can be identified through vibration analysis. Vibration analysis is the best non-destructive test you can perform on a running piece of rotating machinery to determine the damaging dynamic forces that are present. If you have rotating machinery in your facility and are not doing vibration analysis, I strongly recommend that you start. Otherwise, you will not have the ability to determine the possible source of your vibration problem and will only be guessing what's the matter when one of your machines starts going into tilt mode. Vibration analysis is a very powerful diagnostic tool, but some people expect too much from the technology. Here is a list of problems that vibration analysis has a difficult or impossible time detecting. It is very difficult to tell the difference between unbalance, bent shafts, or excessive runout. All of these conditions will exhibit what appears to be an out-of-balance condition, and in fact, permanently bent shafts and excessive runout are out-of-balance conditions. But how you go about correcting these problems would be different depending on what issue it is. To me, it doesn't make much sense trying to balance a rotor that has a permanently bent shaft. Vibration analysis cannot detect leaking bearing seals or leaking mechanical seals, nor can it detect if a journal bearing has mildly wiped. It cannot detect excessive piping strain. It may be able to detect a looseness condition, but it may not be able to tell you what is loose. Vibration analysis cannot tell you if your belt tension is too tight. In some cases, if rolling element bearings have become excessively damaged, like when the balls fall out, vibration analysis is not going to be of much help. Vibration analysis can often detect rotor to stator air gap problems, but it cannot differentiate between an air gap problem and a distorted motor case. The same is true for gears. Vibration analysis can detect gear mesh issues, but it cannot differentiate between a gear mesh problem and a distorted gear case. Vibration analysis cannot detect if a machine is running backwards. It cannot tell you anything about the operational efficiency. Vibration analysis is also not very good at detecting how severe the misalignment is on a drive system. Before we explore this in more detail, let's talk a little bit about the behavior of shafts. Here we have a long piece of pipe supported on two roller stands. If the pipe was infinitely stiff, this is exactly what we would see. But metal is elastic and the pipe is not infinitely stiff. Rather, what we would see is something like this occur, where the pipe bends or sags in the middle from its own weight. If we were to weld a bar on one end of the pipe and put a crank handle on the bar, then grab a hold of the crank handle and begin to slowly rotate the pipe, what would happen? The instant the pipe started rotating, would the pipe immediately spring into a perfectly straight line? No, it wouldn't. The pipe is going to rotate on a curved center line of rotation. What if we increased the rotational speed to, say, 10 revolutions per minute? Would the pipe straighten out then? Probably not. The pipe would continue to rotate on a curved center line of rotation. Is there any speed at which a horizontally mounted pipe that elastically bends from its own weight ever straightens out? The shape of the pipe as it elastically bends is called a catenary curve. It is very normal for a shaft to rotate on a curved center line of rotation. The amount of droop at the midspan between bearing points is typically very slight, especially for short distances between the bearings. But for long spans between bearings, as might be found in the armatures of large electric generators, it is not uncommon to have a sag of 50 to 100 thousandths of an inch or more. This perfectly natural elastic bending of shafts needs to be taken into consideration when aligning two or more shafts where each shaft has a considerable span between the bearings, both of which are elastically bending due to their own weight. Here, for example, we have two independent, infinitely stiff shafts where each shaft is supported in its own bearings. If the perfectly straight center lines of both shafts are collinear, then all four bearings are also collinear. However, we now realize that horizontally mounted shafts elastically bend in a catenary curve. If we intentionally align the bearings so they are collinear, then it becomes obvious that there is a misalignment condition between the center lines of rotation of the shafts. Again, be cognizant of the fact that the shafts shown here naturally want to rotate on their curved center line of rotation. This doesn't look right, so we need to probably raise the outboard bearings a little bit, don't you think? Oops! Here we have over-exaggerated the matching catenary curvature, so the coupling hub faces are further apart at the bottom than they are at the top. Let's try another adjustment. There we go. That looks better, doesn't it? Now the two shafts will rotate on their own natural catenary curve that blends perfectly across the coupling between the two shafts in the drive system. This illustrates the ultimate goal of shaft alignment. What we want is for the shafts to be in line with each other when they are running. Here are two shafts connected together with a flexible coupling. The bearing spans are very short, so for all practical purposes, there is very little elastic bending due to the weight of the shafts. The shafts themselves are not bent, and the coupling hubs have been bored properly, so there is no major runout problems. Let's now take a look at what is going to happen to our shafts if we begin to misalign them. The dashed red lines define the center of the bearings for each independent shaft. What we're going to do here is intentionally begin to misalign these two shafts by lowering the shaft on the right. If there is a slight amount of misalignment, then the flexing points in the coupling should be able to accommodate that with very little trouble. But I also understand that there is a limit to how much misalignment a flexible coupling can accept. What if the misalignment begins to exceed the misalignment capability of the coupling? What if we get to the point where the flexing points lock up and no longer function as they were designed, and we misalign the shafts beyond that point? What happens is the shafts start elastically bending in an S-shaped curve. The greater the amount of misalignment between the shafts, the more exaggerated the S-shaped curve becomes. Be very careful not to misinterpret the illustration. The shafts in the middle and lower position are not permanently bent. They are just elastically bending. There is only a one-letter difference between the words bend and bent, but there is a huge difference in what those two words mean. Also be aware that elastically bending shafts do not produce an out-of-balance condition. If the shafts were perfectly balanced before they were misaligned, they are perfectly balanced now also. The center of mass at every point along the elastically curved shaft is still coincident with the center line of rotation at every point along the shaft. If we disengage the coupling in the extreme misalignment condition shown in the lower two shafts, each shaft would spring back to the dashed red lines which define the center line of the two bearings that support each shaft. If you remember, a short while ago, when we were talking about things that put static loads on bearings, it was mentioned that three very common sources of static forces on bearings were gravity, or the weight of the rotor, belt tension, and shaft misalignment. So let's examine the static forces that are present in these two shafts, and for this discussion, we are viewing the shafts in the side view. The shaft on the left has some weight, so there is a downward force on it due to gravity. Each bearing produces an upward force opposing the gravitational load. Similarly, the shaft on the right sees the gravitational force, and its bearings produce an upward force to oppose the gravitational load on them. If we begin to misalign these two shafts, the flexible coupling accommodates a certain amount of the misalignment, but once that is exceeded, the shafts will start elastically bending. The gravitational forces are still there, but now, through the coupling, the shaft on the right induces a downward force on the shaft on the left. This force now produces an additional force on the inboard bearing in the downward direction, but it will produce an upward force at the outboard bearing. The shaft on the left produces forces on the shaft on the right also. Through the coupling, the shaft on the left induces an upward force on the shaft on the right. This force now produces an additional force on the inboard bearing in the upward direction, but it will produce a downward force at the outboard bearing. If we continue to misalign these two shafts, the shafts begin elastically bending even more. The gravitational loads are still present across the coupling. The downward force on the end of the left shaft has increased, as well as the reactionary forces on its bearings, and the upward force on the shaft on the right has increased, as well as the reactionary forces on its bearings. At the beginning of this tutorial, I asked the question, what will happen if you misalign a drive system? Will the vibration go up, go down, or stay the same? The vast majority of people I asked that question to say that the vibration will go up. Their reasoning, I guess, is that by misaligning the shafts, you are putting a problem into the machine, and therefore the vibration must go up when problems are present. That's what I had thought for a long time, but strange things were happening when I would measure vibration on machinery that I knew was misaligned, and I had some trouble explaining what I observed. To me, the best way to determine what happens is to try an experiment where I intentionally misalign the drive system and observe the vibration before and after I misaligned it. One of the first experiments I tried was with one of our balance and alignment training demonstrators. As shown in the photograph, the demonstrator consists of a 1/2 horsepower, 120 volt single-phase motor running at 3,590 RPM. It is flexibly coupled to a center shaft with 2 balance discs. The center shaft is then flexibly coupled to an outer shaft with an overhung balance disc. I carefully balanced the center and outer shafts to minimize any unbalanced influence in my experiment, so I could hopefully only see what effect misalignment had. I also did not have any concrete proof at that time that shafts will elastically bend under misalignment conditions, so I decided to try and measure if any deflection in the center shaft would occur when I intentionally misaligned it. To measure any deflection, I attached a bar to the bearing housings that supported the center shaft, drilled and tapped 2 holes in the bar right where the balance discs were located, and installed proximity probes into the threaded holes. Another question that was being discussed at that time was, does it take more energy to run a drive system misaligned compared to aligned? So, at each step of the experiment, I also measured the current draw on the motor using a clamp-on ammeter. The test was fairly simple. The motor, center shaft, and outer shafts were aligned within 0.2 of a mil per inch in both the vertical and lateral directions. I then started the drive system up and, using an accelerometer with a magnetic base, measured the amount of vibration on the bearings on the motor, center shaft, and outer shaft in the vertical and horizontal directions. I also took axial vibration measurements on each of the components. I then measured the amount of current draw on the motor and measured the gap voltages on both proximity probes, observing the position of the balance discs on the center shaft. The training demonstrator was then shut down. I loosened the 4 bolts on the center shaft and, using the jack screws, translated the center shaft 31 mils sideways for the first misalignment test. There is a 1.5 inch separation between the flexing points and the disc-type couplings. With 31 mils of misalignment, there was then slightly over 20 mils per inch of misalignment at both couplings. I started the drive system back up and measured the vibration, motor current, and proximity probe gaps again. The training demonstrator was shut down again. I then loosened the 4 foot bolts on the center shaft and, using the jack screws, translated the center shaft another 31 mils sideways for a total of 62 mils of lateral misalignment, which resulted in slightly over 41 mils per inch of misalignment. I started the drive system back up and measured the vibration, motor current, and proximity probe gaps again. Here is the results of the experiment. For you vibration people, the overall vibration data units are in inches per second peak for all the measurements. Starting with the outboard bearing on the motor in the vertical direction, when the motor was well aligned, the overall vibration was 0.040 inches per second. When the center shaft was misaligned 31 mils laterally, which is called test A, the overall vibration dropped to 0.031 inches per second. Then for test B, when the center shaft was misaligned 62 mils laterally, the vibration dropped again to 0.027. In the horizontal direction, from well aligned to test B, the vibration levels went from 0.044 to 0.031 to 0.030. In the axial direction, well aligned to test B, 0.040, 0.029, 0.029. At the inboard bearing, in the vertical direction, 0.037, 0.029, 0.027 inches per second. On the center shaft, at the bearing on the motor side, in the vertical direction, from well aligned to test B, 0.037, 0.027, and 0.029. Notice that the overall vibration here from test A to test B increased from 0.027 to 0.029 inches per second, but it never got back to 0.037 when it was well aligned. In the horizontal direction, the vibration went from 0.039 to 0.028 to 0.036. In the axial direction, 0.035, 0.032, 0.028. On the other bearing in the vertical direction, 0.035, 0.028, 0.026, and in the horizontal direction, 0.037, 0.029, 0.028. On the outer shaft at the bearing and the coupling side, in the vertical direction from well aligned to test B, 0.031, 0.028, and 0.027. In the horizontal direction, the vibration went from 0.037 to 0.029 to 0.032. On the outboard bearing, in the vertical direction, 0.036, 0.028, 0.027. In the horizontal direction, 0.035, 0.029, 0.030. In every case, the amount of vibration was lower when the unit was misaligned than when it was well aligned. And in the majority of the cases, the more I misaligned the drive system, the lower the overall vibration got. What did the proximity probes see? Here is the gap voltages and corresponding gap distances from the probes to the balance discs. The probe on the left I called probe 1 and the probe on the right as probe 2. At probe 1, when the unit was well aligned, the gap voltage was minus 9.8 volts DC. At probe 2, when the unit was well aligned, the gap voltage was minus 9.49 volts DC. Since these were the gaps when the unit was well aligned, I just called them the zero or starting position. The proximity probes had a sensitivity of 200 millivolts per mil, so for every 1 volt change, the distance from the probe to the surface would be 5 mils. For test A, when the center shaft was misaligned laterally, 31 mils, The gap voltage at probe 1 increased to minus 10.27 volts DC, and the gap voltage at probe 2 increased to minus 10.06 volts DC. With the 200 millivolt per mil sensitivity, the resulting gap change at probe 1 was 2.35 mils, and at probe 2, 2.85 mils, with the balanced discs moving away from the probes. For test B, when the center shaft was misaligned laterally 62 mils, the gap voltage at probe 1 increased to minus 10.88 volts DC, and the gap voltage at probe 2 increased to minus 10.72 volts DC. The resulting gap change from well-aligned to 62 mils of lateral misalignment at probe 1 was 5.4 mils, and at probe 2, 6.15 mils, with the balanced discs moving away from the probes. Now, how could this have happened if the shafts were not elastically bending? Also notice that the worse the misalignment got, the greater the elastic bending occurred in the center shaft. One last item here. What happened to the current draw on the motor? Does it take more power to run machinery misaligned compared to well-aligned? When the motor was well-aligned, the amperage was 3.58 amps. When there was 31 mils of lateral misalignment, the amperage draw was 3.63 amps, and when there was 62 mils of lateral misalignment, the amperage was 3.60 amps. Hard to draw any conclusions here, except that it doesn't appear that misalignment had much of an effect on the power needed to rotate the shafts under any type of alignment condition. So, to summarize the results of this experiment, I suppose we can say that the vibration levels decreased when the drive system was misaligned. The center shaft appeared to elastically bend, and the amount of elastic bending increased as the misalignment increased, and there didn't seem to be much of a change in the amount of power requirements to operate machinery running misaligned. For the majority of the people I know, all three of these discoveries come as a major surprise. Yet I know of many people who are using vibration as a means to ascertain the accuracy of alignment on operating rotating machinery. I'm not sure that's a good idea. What do you think? A few years prior to the misalignment experiment on a training demonstrator, I did my very first misalignment experiment on a motor-driven circulating water pump. To my knowledge, it may have been the first time anyone intentionally misaligned a drive system and observed what happens to the vibration. Initially, I did it to prove, once and for all, that vibration increases when you misalign machines and that misalignment will show up at twice running speed. Boy, was I in for a surprise. There were 4 different misalignment conditions that I tested. Initially, the drive system was aligned within 0.2 mils per inch. Then, I misaligned the motor sideways by 21 mils, started the pump up, gathered the vibration data, and shut the unit down. I then misaligned the motor until the motor got bolt-bound at 36 mils of lateral misalignment. I started the pump up, gathered the vibration data, and shut the unit down. I was kind of disappointed that I could only get 36 mils of misalignment, so I decided to misalign the unit vertically also. There were 55 mils of shims under all the feet of the motor, so I took them all out. I started the pump up, gathered the vibration data, and shut the unit down. Then I put the shims back in and added 65 more mils of shim stalks so the motor was high with respect to the pump. I collected both overall vibration measurements and vibration spectral data. For this tutorial, we will look at just the overall vibration data. The vibration spectral data will be discussed in a tutorial in the Category 4 Shaft Alignment Training Series. Starting at the coupling, or inboard end of the motor, the overall vibration in the horizontal and vertical direction started out at around 0.05 inches per second and remained pretty much at that amplitude level for both the 21 and 36 mil lateral misalignments. There was an increase in amplitude when the motor was 55 mils low, but then, surprisingly, at the worst misalignment condition, where the motor was high by 65 mils, the vibration in the horizontal direction decreased slightly. At the outboard end of the motor, which has the horizontal, vertical, and axial vibration, a similar trend occurred, where the overall vibration levels didn't increase until the motor was 55 mils low. For the test run when the motor was high by 65 mils, the vertical and axial vibration increased slightly, but again, for some reason, the horizontal vibration decreased. At the inboard or coupling end of the pump, when the unit was misaligned 21 mils laterally, the vibration decreased in the horizontal, vertical, and axial directions. At 36 mils of misalignment, the vibration increased in the horizontal and axial directions, but still didn't get back to the well-aligned vibration amplitude in the vertical direction. At 55 mils low, all three amplitudes increased, and here is where the vibration was at its highest amplitude at any bearing. But then, in the worst misalignment condition, where the motor was 65 mils high, the vibration decreased. As you can see, the outboard bearing of the pump had a similar pattern to the overall vibration. Now, what conclusions can we draw from this experiment? Well, there doesn't seem to be a linear relationship between the amount of misalignment that is present and the amount of vibration you see. For example, if you had 10 mils of misalignment on a drive system and measured the vibration on the bearing housings, then shut the machine down and doubled the misalignment to 20 mils, the vibration will probably not double. The other conclusion is that if you misalign a drive system, it is possible for the vibration to decrease, as seen in the pump bearings from a well-aligned condition to a 21 mil lateral misalignment. The other conclusion is that if you have a fairly severe misalignment condition, like the 55 mil low misalignment on the motor, and increase the severity of the misalignment even more, the vibration can still decrease. So, to me, I don't think that attempting to use the amplitude of vibration to determine the severity of a misalignment condition is going to ever tell us how bad of a running misalignment condition we have. Much of the mechanical deterioration and eventual damage to our rotating machinery can be attributed to the static and dynamic forces acting on our machines. Forces that are changing their direction or periodically increasing then decreasing are defined as dynamic forces. Dynamic forces are the source of the vibration that occurs in our machinery. Vibration analysis is a powerful diagnostic tool and can assist us in determining what might be causing the vibration to occur. Accelerometers, velocity sensors, and proximity probes measure vibration. They do not measure force directly. In addition to the dynamic forces, static forces are present also. These forces act in one direction and, if severe enough, can elastically bend or deform an object, like a shaft. The downward force from gravity is one type of static force but other situations can produce static forces in a sideways or upwards direction. If static forces are acting in different directions, the shape of the shaft will not necessarily be a catenary curve, but could also exhibit a sinuous or wavy shape. As we've seen in the intentional misalignment experiments, there does not seem to be a linear relationship between the amount of misalignment and the amount of vibration. If you double the misalignment, the vibration may not necessarily double and in fact may decrease rather than increase. Therefore, it is important to recognize that if you measure the vibration on a drive system that is operating in a misalignment condition, shut the unit down, align it correctly, start it back up, and measure the vibration again, it is possible for the vibration to increase, making it look like you did the alignment wrong. Well, hey, thanks again for your interest in machinery alignment, and I hope this information has prompted you to want to learn some more.